Hello, this is Dylan Blair. As I mentioned in the previous video, we are now done with 9.1, but we're going on to 9.2, and this is hopefully a way to resolve our issue of the lecture videos not being recorded. So let's scroll through what we've already covered. Okay, so now we're to 9.2, the unit vector. So a unit vector is a vector whose magnitude is of length 1. Okay, so not all vectors are going to be unit vectors. Actually, we'll kind of scroll up to where we left off with last time when we talked about magnitude and the angle of a vector. This guy, this cosine of theta, sine of theta, actually ends up being a unit vector because this vector right here ends up falling on a unit circle, right? Where here's the center of the unit circle, and that arc, that radius, that vector ends up just being a radius of 1 all the way around no matter where you point it, okay? And as I'm getting to, we denote a unit vector with a caret hat, okay? But since all vectors aren't already unit vectors, we can create a unit vector by dividing or scaling down a vector by its magnitude or its length, okay? So we're essentially kind of dividing. We're not dividing, we're scaling by 1 over that magnitude, so that if v is equal to a comma b, then this means that v scaled down by the magnitude of itself ends up being a over the magnitude of v, and then b over the magnitude of v. Okay, so if it's already a unit vector, you're just going to be, that magnitude is going to be 1 because the length is 1. And so you're going to be taking a over 1, comma b over 1, which is just still a over b. So it doesn't really matter. You're just kind of doing a redundant process at that point. But if you're in, like, say, a computer program and you wanted all of your vectors to be unit vectors, you don't have to worry that you're going to mess up if it already is a unit vector. And ultimately, what a unit vector does is unit vectors are good for certain calculations. It's a little bit more beneficial when you're talking about in terms of how you use them in linear algebra context. But for the purpose of this class, it's going to be more so the next slide. It gives us another vector notation, which you'll see here in a second. But either way, a unit vector always still points in the same direction, okay? Because we define that direction by that angle theta, right? It's not that a and that b. That a and that b are just scaled down the exact same amount, right? So this new component is a over magnitude of v, and this new component is b over magnitude of v. And so they're scaled down the identical amount, and so that means that their angle is the exact same. So they still point in the same direction. The one is just a length of 1 or a magnitude of 1, whereas the other one is not. Okay. Alrighty. Now, the kind of purpose behind how we use unit vectors for this class is a little bit easy. So it's kind of nice to kind of introduce you guys to unit vectors in this sense. But what we have are what's known as principal unit vectors. So now that we know what a unit vector is, we have two principal unit vectors in a two-dimensional Cartesian coordinate space. Okay, so we have these principal directions, our x direction and our y direction. So we're going to define principal unit vectors in each of those directions. So we're going to have what's known as I, which is going to be in our x direction. Okay, so I in our x direction. And so that means that we're going to go 1 to the right and 0 upward. So we're only pointing to the right, right? And we can check to see if this is in fact a unit vector by taking the magnitude. So it's going to be square root of 1 squared plus 0 squared. So it's going to be the square root of 1, which is just equal to 1. So it is a unit vector. And that one's a trivial one to see. We can see that it has a length of 1 because it's only pointing to the right by 1 and no vertical component. Okay, and j with caret hat is similarly just doesn't point to the right or left, and it only points up by a magnitude of 1. Okay. So now, how we can use these principal unit vectors is we can rewrite our base vector notation to a decomposed principal unit vector notation, so that we can say our vector A that has A naught and A1, we can say that this is A naught scaling our principal unit vector in the I direction, plus A1 scaling our principal unit vector in the j direction. So this is just A naught scaling 1, 0 plus A1 scaling 0, 1. So if we were to distribute these back through, we just have A naught, comma 0 plus 0, comma A1, and A naught plus 0, so we add them component-wise, is going to give us A naught. 0 plus A1 is going to give us A1. Okay. So now that's basically all we did here, is we can say if this is our principal unit vector down here for I, and this is our principal unit vector right here for j, we can scale this guy. I don't need to write this. We can scale this I by A naught so that we get this result, and we can scale this guy by A1 so that we get this result. Then when we add head to tail A naught I plus A1j, we're going to be following along this path until we get that original vector A. Okay, and similarly, if we were to go the other way, if we wanted to do A1j plus A naught I, we'd be going head of this vector to the tail of this vector to get the same result, and we get that nice geometrical representation that we had talked about before in the previous slides. Okay, now we are going to talk about how we can add and scale vectors when they're in this principal unit vector notation. Okay, so just like vectors in our caret bracket notation, we need to add component-wise. Okay, so when we're adding, we're going to have A naught plus B naught. Did not mean to do that in color. A naught plus B naught and A1 plus B1. So we'd have A naught plus B naught scaled by I and A1 plus B1 scaled by J. And it's as simple as that. Okay, when we're scaling, we're going to take the results of these two and we're going to scale both our I and our J component. Okay, and subtraction works the exact same way. And that is it for our section 9.2. So I will see you guys here shortly to finish up with 9.3 on dot product.